Hey, hello everyone. Welcome to our channel Physics, where we actually learn physics. Now, in this lecture, we will be solving this problem that you see. It is 2.28 from chapter 2 actually. That is nothing but units and measurements. Okay, from 11th standard CBSE. Okay, the question is, the unit of length convenient on the nuclear scale is a Fermi. Okay, the unit of length convenient on a nuclear scale is a Fermi. That means on the nuclear scales we use unit called as Fermi. 1 Fermi is equal to 10 raised to minus 15 meters. Okay, this is a very standard equation. Okay, 1 Fermi is equal to 10 raised to minus 15 meters. Nuclear sizes obey roughly following empirical relation. So all the nuclear sizes, they generally obey this equation that you see over here. Okay, this equation is very important that you see. So every nuclei obey this. That means the radius of any nuclei can be found out using this. Only thing is you have to put this value and this value. See, every nucleus has got some mass number A, right? For example, carbon 612. So this mass number A is 12. Oxygen 816. So A over here is how much? 16. Okay, uranium 236. What is A? 236. Okay, so in this way, every nuclei has got its mass number. Okay, so now what we have to do is over here we have to just put this value of A and R naught. Now what is R naught here? See, where R is the radius of the nucleus and A is the mass number, as I said, and R naught is called as the constant equal to about 1.2 Fermi. Okay, R naught is a constant equal to 1.2 Fermi. 1 Fermi is equal to how much? 10 raised to minus 15 meters. That's why it is 1.2 into 10 raised to minus 15 meters. Okay, so this is the value of R naught. So we just have to put all these values and you will get the radius. A is bigger for bigger nuclei, right? So that's why the radius will also be bigger over here. Over here actually we have to show that the rule implies that nuclear mass density is nearly constant for different nuclei. That means we have to prove that according to this relation, the nuclear mass density is almost constant for every nuclei. Okay, that means every nuclei has got same mass density. This is what we have to prove from this equation. Okay, estimate the mass density of sodium nucleus and compare it with the average mass density of the sodium atom, not nucleus, it is atom. You know the difference between atom and nucleus. Okay, mass density of a sodium atom obtained in exercise 2.27. That means in the previous exercise we have actually obtained the value of average mass density of sodium atom, and that is, I will write here, rho atom is equal to 0.6 about. Okay, this is nearly 0.6 into 10 raised to 3 kg per meter cube. So that was the value that we obtained. So we have to now compare. We have to compare the mass density of sodium nucleus with the average mass density of the sodium atom. Okay, that means density of the atom of sodium and density of the nucleus of sodium. That is what we have to compare. Okay, so let's do this. First of all, we have to show that this rule implies that the nuclear mass density is nearly constant for different nuclei. Okay, so let's do this. So what is density? Density is equal to mass per unit volume. Okay, now we want to talk about the mass of a nuclei. Now we know any nuclear species is represented like this, Za. For example, it is copper, so it is 2963. Z here is 29 and A here is 63. Okay, Z is nothing but the number of protons. Okay, here there are number of protons is represented by Z, and the number of neutrons are represented by n, and the mass number is represented by A. Okay, is represented by A, and we know A is equal to n plus z. That means number of neutrons plus number of neutrons will give us the mass number A. Okay, so this is something that we already know. Okay, now suppose you have any nuclei. Let's say for example this one, copper. Okay, so here you can see there are protons, and how many are the neutrons? Just 63 minus 29, it is 34. Okay, 34 neutrons and 29 protons. Now suppose you want to calculate the mass, okay, mass of this copper nucleus. So we must know the mass of one proton and mass of one neutron. So the mass of one proton is 1.67261 into 10 raised to minus 27 kg, and here it is 1.67492 into 10 raised to minus 27 kg. So you can see here that roughly they have same masses, almost same masses. We can say here MP is nearly equal to Mn. Okay, MP is nearly equal to Mn. We can call this as small m, and we can just write it is as 1.67 into 10 raised to minus 27 kg. That is the mass of protons and neutrons roughly. Okay, we are considering them nearly same actually, because they are almost same. Okay, very small difference you can see here, very in fact there is a 10 raised to minus 27 also. So you can imagine the difference in mass is at what decimal place. Okay, you have to go 27 decimal places back. Okay, then you will understand where is the difference, at what decimal place. Okay, anyways, so we are just considering them same. Okay, now suppose you want to find out the mass, total mass of any nucleus. So that would be nothing but number of protons times the mass of protons plus number of neutrons times the mass of neutrons, right? So over here number of protons may be any value for any particular nuclei. If I consider over here this copper, number of protons are 29, number of neutrons are 34. But right now let's keep it a general equation. But over here I said that they are equal, nearly equal. So we can see here Z plus N, M will be common because this MP and Mn, they are nearly equal, and we have indicated this by small m. Okay, so we just writing this outside the bracket as a common. So mass or the total mass of any nucleus is Z plus N times M. Now what is Z plus N? Nothing but A, isn't it? It is A times M. That means total mass is equal to M times A. Okay, for any nuclei. Okay, for any nuclei. Now this is mass. Now let's talk about the volume. Okay, because we want the volume also. So volume is equal to what? See, nuclei is roughly a spherical body, right? So spherical bodies have a volume of 4 by 3 pi r cube. Okay, now r is given, r is equal to r naught a raised to 1 by 3. So we want r cube, so we have to just raise the power by 3 on each side. So here when we raise the power by 3, so here there will be 3. So 3 by 3 is 1. So this will be our answer. So r cube is a times r naught cube. Okay, that is r cube. Now let's put this value in our equation over here. So volume will be equal to 4 by 3 pi. Okay, let me differentiate this first of all. Okay, pi r cube. R cube is a r naught cube, right? See here we have put the value of r cube from this equation over here. Okay, so we have got this 4 by 3 pi a r naught cube. Now we have got mass as well as volume. Now we are ready to find out the density, right? We can find out the density. So density is equal to mass per unit volume. See here, now we have the equation for mass. Mass is ma upon density is 4 by 3 pi a r naught cube. So you can see this A cancels, right? What remains over there is this. Rho is equal to m upon 4 by 3 pi r naught cube. Look at this equation. In this equation, all the terms are constant, isn't it? All the terms are constant. This means what? This means that nuclear density, okay, or nuclear mass density, okay, nuclear mass density is constant for all the nuclei, because you can see here we are getting a constant number, isn't it? All these terms are constant, isn't it? So that means what? That means over here it is a constant number. Okay, every nuclei has got same density, almost same density we can say. So in this way we have actually proved this fact which was asked over here. What was asked here? Show that the rule implies that the nuclear mass density is nearly constant for different nuclei. And here it is, we have proved it. Okay, see, if the nuclear density was different for different nuclei, then there would have been some term here related to the nuclei. Okay, like there should have been Z, there should have been N, there should have been A, something like that. There should have been something over here if it was, okay, it was different for different nuclei. Okay, if it was different for different nuclei, then there would have been some term relating to that nuclei in this equation, but it is not there. You can see it's not there. This equation does not contain any particular term that talks about any particular nuclei. So that's why this equation is a very general equation, very constant equation. Okay, a firm equation actually. It does not change. You can see. Okay, because there is no variable here. Everything is constant over here. So that means that the density is, nuclear mass density is constant for all the nuclei. Okay, so let's calculate this value and let's see what it is. So mass, what is mass? It is 1.67, isn't it? 10 raised to minus 27. We have just seen this. Here it is. This is 1.67, isn't it? Divided by 4 by 3. 4 by 3 will be written here, right? Okay, into 3.14 into R naught. What is R naught? R naught is 1.2 into 10 raised to minus 15, right? In meters. Now we have to cube this. So it is 1.2 cube into 10 raised to minus 15 cube. What it would be? It would become 10 raised to minus 45. It is minus 45. Okay. So this is what it becomes. Okay. So I hope this is clear. Now we can calculate what this can be. Okay. So let's use our calculator. Here it is. Okay. One thing we can do is we can first of all cancel these terms. 10 raised to minus 45 minus 27. Now what will prevail here is 10 raised to 18, I guess so. Right? You can check that, because when this term will go up, it would be 10 raised to 45 into 10 raised to minus 27 is already there. So 10 raised to 45 minus 27 is nothing but 10 raised to 18. Okay. So this would be our answer. Okay. So this term is gone from here. Okay. All these terms is gone. Okay. So now we are just left with this part. Okay, so it is 3 times 1.67, okay, equal to 5.01, right? So I will write here 5.01 into 10 raised to 18, all divided by this. Let's multiply this. First of all, 1.2 cube. So 1.2 cube, okay, this is it, into 3.14 into 4 equal to what? This 21.70. Okay, right now we are not concerned with the significant figures, so let's not care about that right now. So it is 21.70. See, we are not concerned with the significant figures for some reason, because we are just estimating actually. We are not talking about the exact measurements. This is just some approximation actually. Okay, so in this way we have calculated this. Now let's divide this. Okay, let's divide this. So it is 5.01 divided by 21.7. Okay, 70 or whatever. Yeah, you can see here 0.23. Okay, we can write this as 0.23 into 10 raised to 18, or we can write this density as rho equal to 2.3 into 10 raised to 17. See, we have shifted 1 decimal place. Okay, so you can see this is the nuclear mass density for any nuclei in nature. Okay, because we have seen that every nuclei has got constant or same nuclear density, nuclear mass density. Now in the question we have to also find out, estimate the mass density of sodium nucleus. We have to find out the mass density of sodium nucleus.